Welcome to Calc-Chat with your hosts, Reagan Burns and Cody Spitzer.
Today we are going to explain how to find the volumes of solid three-dimensional objects using aerial cross-sections.
But first we need to ask ourselves, what is a cross-section?
Dictionary.com defines a cross-section as a section made by a plane cutting anything transversely, especially at right angles to the longest axis. In other words, a cross-section is a crosswise slice out of a 3D object.
Imagine a loaf of bread. If you cut the three-dimensional into virtually two-dimensional slices, each slice is now an aerial cross-section of that loaf of bread.
Cross-sections can be various shapes. In calculus, cross-sectional areas are often represented by squares, rectangles, triangles, or semicircles.
Now that we've fully grasped what a cross-section is, we may begin using them to find volumes of 3D figures.
Take the square pyramid, for example. What does its cross-section look like? A square. What is the area of each cross-section? The side of the cross-section squared. Finally, what is an integral expression that could be used to find the volume of the figure? The derivative of the volume of the pyramid is equal to the integral from a to b of the square of a side of the cross-section times the derivative, or rate of change, of the height of the pyramid.
Take the two functions y equals x and y equals x squared, for example. It is first important to find where these two intersect by setting them equal to one another, and you'll find that they intersect at 0 and 1, which tells you that your interval is also 0 to 1, which is important because that's the interval that you will be integrating.
The area between these two graphs represent the base of the solid. If you take the cross-section of the solid, you'll find that it's a square perpendicular to the x-axis. To find the area of a square, you take one side of the square and square it. To find one side of the square, in this case, you would take the upper graph minus the lower graph, which would give you x minus x squared. Therefore, your area is x minus x squared squared. Then, to find the volume of this solid, you would take the integral of 0 to 1, your integral, of the area x minus x squared times the derivative of x.
Now let's say you're asked to find the volume of the solid using the cross-section semicircles. Much like a circle, the area of a circle being pi r squared, the area of a semicircle is simply 1/2 that of a circle, so it's being 1/2 pi r squared. In this case, the upper curve minus the lower curve would give you the diameter of the semicircle. But what the equation asks for is the radius. So the radius would equal 1/2 of the upper curve minus the lower curve. Knowing this, we can define the area of the cross-section as 1/8 pi times the upper limit minus the lower limit, which is x minus x squared, and then all that squared. Then we can find the volume by integrating from 0 to 1 of the area 1/8 pi times x minus x squared times the derivative of x.
This time, the area between the two curves will still represent the base of the solid, but the cross-sections will be equilateral triangles parallel to the x-axis. To find the side of the triangle parallel to the x-axis, you must rewrite the equations in terms of y. Therefore, your equations will be x equals y and x equals square root of y. So therefore, one side of a triangle will be the square root of y, the furthest graph, minus y, the closest graph. Therefore, the area of the equilateral triangle will be root 3 over 4 times root y minus y squared. Then you can find the volume by taking the integral from 0 to 1 of root 3 over 4 root y minus y squared dy. It is important to note that when you're taking cross-sections parallel to the x-axis, they vary by dy, or the rate of change in y, rather than dx, the rate and change of dx.
Now let's say you're asked to find the volume of the solid by using the cross-sections of rectangles with a set height of 2. Now normally, the area of a rectangle is defined by length times width. In this case, length times height. And the height in this scenario is set at h equals 2. And the length is set by the upper curve minus the lower curve, the upper curve being y equals x and the lower curve y equals x squared. So the area can be defined in this scenario as area equals x minus x squared times 2. Therefore, the volume is equal to the integral from 0 to 1 of 2 times x minus x squared dx. And then all you have to do is bring the 2 out in front, and you can integrate the problem. Now it's time for everybody's favorite, the calculus joke of the day.
Why is beer never served at a math party? Because you can't drink and derive.
As always, thanks for watching, and tune in next week to learn about volume by disk and washer method.